It's great to be here, and it's also great to be building on everything that you guys have been learning. And I come from, as you can tell from Turi's introduction, I'm a geologist. I come from this perspective of trying to understand past climates and past systems. However, I had my office as a graduate student in South Biology in Turi's lab, and basically all of my friends were ecologists, and I had a meteorologist on my committee. And if you're really going to try to understand what past climates and past environments and past ecosystems are like and use isotopes to do that, well, you better understand how those isotope systems are working today, right, in order to translate into the past. And if you're going to push the limit, right, and do anything new, then you got to really figure out how those systems work today. So my goal, unabashedly, is I'm really just intrigued by past climates and past environments. But I am very honest with myself that I can't understand that unless being very, very anchored in modern processes today. So hopefully that will come through in this talk, but hopefully the kinds of things that I'm talking about will apply to all of you, whatever your interests are. Okay, so the objectives of what I'm going to talk about today. I want to give you guys some exposures to different ways of thinking about isotope distributions other than just heavy to light. So right now we've been thinking in this delta notation and delta values, and there's a tremendous amount that can be done. But I want to blow your mind today, and I want to make you think whoa, there's even more that can be done, like that really annoying 17.0 correction that I have to do. There's actually useful information that's riding along, and if we just spend a little bit more time, a lot more time making the measurement, we might be able to get something useful. That's exciting, okay? So I want you guys to sort of this stuff is hard for people who have been thinking about this stuff for a long time, so I don't expect to get everything, but I just want you to get you thinking about how these isotopes might apply to your research, because I find that when I start to think about problems that I can, my brain has limited capacity, so if I can kind of think about systems in a way that in a space that I feel comfortable in, then I might be able to internalize them a little bit more. So if you feel overwhelmed by this material, don't sweat it, because you're not going to get all of it. It's just too much to get all right away, so don't bother. Just sit back, try to think big picture, and prime yourself for keeping to think about new ideas in the literature. And I hope that it can be an inspiration to kind of think about that. You're comfortable, you're working on these new systems, but there's a lot out there, and the field is developing really fast. And so I assigned 2 readings. One was this Frontiers, as I hit myself in the, okay, so by John Eiler. There's a review paper, Frontiers in Stable Isotope Geoscience, but don't worry about, if you're like, but I'm an ecologist. It's like, well, just, don't put yourself in that bin. There's really exciting things that, no, and I'm serious, it's like there's so many different kinds of questions, and the overlap between, biology and geology and chemistry and physics, it's just like, you just can't worry about, the bin you fit in sometimes. Anyway, so this is a really good review paper. It's totally dense, but it has references to the concepts that I'll talk about. And then the other paper that I assigned is a paper by my student, Xuning Li, who did on 17.0 in waters and tap waters, which will be a little bit more of an accessible way to approach it. And then I also, hopefully it's posted, and if it's not, we'll get it. All of the references that I provide in the talk, and there's a whole reference list of all the citations and stuff. But, okay. So why am I motivated to work on something, to do something a messy, harder system? Part of it is my brain is happy being in complicated, hard things, and that's part of it. But so these are the kinds of systems I work in the geologic record. I use fossil soils to try to understand the vegetation distribution and water stress and fossil landscapes. These are lake cores from southern Kenya. We try to reconstruct records of climates in the past. This is a big cut. This is a soil and a floodplain, another soil. Jay Quaid, for those of you who know him, is right there, so that's for scale. Anyway, I work in lots of different kinds of materials, and I work in modern systems, and I work in geologic systems, so in order to understand fossil teeth and how they work, we've done a lot of work in modern teeth in Africa. We've worked in waters, but the whole idea is trying to get more information out of the fossil record. And when you're working with carbon, is more or less straightforward, but oxygen isotopes are really complicated. There's lots of different things that can tweak those levers. So in all papers that look at certainly terrestrial systems and oxygen isotopes, the conclusion is well, it could be 3 things, but for this reason we think it's this one. We like solution B, but it's like not totally satisfying, and there's all these other, there's too many degrees of freedom in the system to really answer it, okay? And so this is why I was motivated to get into, to try to measure 17O, because I thought that maybe I could try to help constrain some of these questions about past climate change in Africa or elsewhere in terms of how arid was it, what was driving change, was it, were oxygen isotope changes that happened in this part of Ethiopia, or is it because it was getting drier, or was it because there was actually a moisture shift and this Congo air boundary shifted, and so it was a moisture source shift that actually changed the oxygen isotopes? And I can't answer that with delta 18 alone. So I basically reached the limit after my PhD, and I was like, we need to do something more. Okay, so this is how I'm going to take you through a terminology review. I can't talk about this stuff without talking about non-mass dependent fractionation, just because it's a huge field out there, and you guys should know that there's fractionation that exists that's independent of mass, right? You should just be aware of that. Then looking at specifically, we'll delve into triple oxygen isotopes, so just the basics, and I'll talk about sort of how it works. Focus on waters, because that's something everybody can relate to, and hopefully that's something that you can kind of think about. And then if we get time to, I'll talk about how we're starting to pivot to applications in paleoclimate. This is where I want to go, and I've been spending the last 8 years sort of getting to this. We're now just getting to this, okay? I started my postdoc in 2008 working on this stuff, and we're now just getting to that, okay? But we're there. So I think all that work and the modern systems and the methods have really taken us to where we can go. Okay, these new capital delta systems, and I'll refer to CAP 17O, and what I mean by that is capital delta 17O. But they can provide, and Katie Snow will talk more about this, but we're sort of looking at more like deviations from some sort of expected relationship. But they provide additional constraints on temperature, kinetic effects, photosynthesis, microbial processes, and likely more. So there's a huge range that we're sort of starting to delve into. We have some sort of expected variation between delta values, and now we're looking at the deviation from that expected. So they've been used in terms of gases that it can be measured, has already been, or not, this is not a gas obviously, but materials, so CO2, carbonate, water, O2, methane. People can sort of start to explore these things because you know the fundamentals, you're willing to push the limits of mass spectrometry and your inlet system, so basically how to get your sample into a form that the mass spec can take it, and you can think creatively about processes within, and maybe that's not without expertise, but within and outside of your expertise, okay? So this is sort of I'll come back to this slide, but hopefully this will resonate with you. Okay, big delta. So I know you guys have been looking at big delta as the difference, just the subtraction between two delta values. This is not it, okay? So in this case, capital delta, we're really looking for some sort of deviation from some expected relationship. So for this purpose, this capital 17O is, which I'll refer to as cap 17O, it's also referred as cap is 17O excess, is the little delta 17O minus, it's basically, it's the intercept, it's what we expect. So maybe I'll sort of write it like this. We actually expect that delta 17O, this is an approximation, is really half of what your delta 18O is, okay? That's what you sort of expect it to be. You should expect that, and so basically why measure it if it's just half is, if your delta 18O is 4 per mil, well then your delta 17O is 2 per mil, you're done. There's no more information in there, okay? The cap 17O of this is the residual from what you actually measure from what you would actually sort of expect, okay? So it's a deviation from an expected. Clumped isotope geochemistry are looking at multiply substituted isotopologues from an expected stochastic distribution, and we'll go into what that sort of means. We'll go into more terms. So an isotopologue, right, is, you guys have actually all been looking at isotopologues. What's somebody's favorite isotopologue? So 2 or more variants of a molecule that differ in the isotopic identity of one or more of their constituents, okay? So a CO2 with 12C, 16O, 16O, that's one isotopologue. A 13C, 16O, 16O is another isotopologue. You guys have been working with isotopologues. It's like Turi's story when somebody came in from the animal control people, and they were like, isotopes? Who's using isotopes in this building? And it's like, they're everywhere, okay? Isotopologues are everywhere. Clumped isotopes are multiply substituted isotopologues. So this is when isotopologues that contain 2 or more rare isotopes. So what would that be for in CO2? What would be an isotopologue of multiply substituted isotopologue of CO2? Yeah, and what would be an even rarer one? Not 13, 18, 16, but 13, 17, 16. Okay, that would be a super rare isotopologue. Okay, but now we're thinking about abundance, as you can imagine. These multiply substituted ones, they're rare, right? Okay, isotopomers, structural variants of an isotopologue. Okay, that differ in the symmetrically non-equivalent location of an isotopic situation. So for N2O, 14N, 15 and 16O is different from 15N, 14N, and 16O. They're isotopomers because the 15N items are in different and symmetrically non-equivalent positions, okay? And why do we care about fractionation? That means that that molecule and whatever it's doing is gonna do something different depending upon where that 15N is, okay? And that's something that can track. So this is the isotopomer is like where you are and where that isotope substitution is makes a difference, okay? So in contrast, 18O, 12C, and 16O, and 16O, 12C, and 18O are not isotopomers because those are equivalent positions where those 18Os are substituting, okay? So it's just a single CO2 isotopologue. Stochastic distribution is something that, and I'm sure Katie will talk about this, but just in sort of, it's a state in which all of the stable isotopes of a population are just randomly distributed, okay? So it's just like, you know, you have mostly brown M&Ms, and you take that, you know, red M&M and that blue M&M, and you just sort of scramble them all together, and the chances that you're going to get an isotopologue, you're going to get a multiply substituted isotopologue, is just a function of how many rare ones are in there, okay? It's that random sampling. But the rub is that, you know, there's actually processes that make the clumping non-random, okay? And that's the process. So a process that Katie will talk about is temperature that makes those heavy isotopes, those rare isotopes come together when you actually, in a non-random way.